Welcome to a model of three faults. Now, you've already finished the actual lab, so this is just the answer key. So for the very first one, you're supposed to locate points A and B, and you're supposed to move point B so that it's next to point A. So it should look like this. So now let's look at how you answered the questions. So the first question was, which way did point B move relative to point A? Well, it moved down. It slipped down. So what happened to rock layers X, Y, and Z? Well, if we look at them, they broke, they slipped, they fractured. So there's lots of things you could talk about, but the easiest thing to just say is they move vertically. They moved, they shifted. So here it says they all shifted vertically. Are the rock layers still continuous? Well, if we look at it like this, they're connected, but it's not continuous like it was when both sides were level with each other. So no, they're not continuous. So what likely happened to the river, the road, and the railroad track? So look at the top of it and look at it from the side. So depending on how you look at it, there's this gap right here. So it's going to change. Now if we go down a little bit, and if the water's flowing in this direction, and look at your model to make sure, but this would tell you that it would be dammed up. So the river will change directions or flood the area. The road will be cracked. The railroad tracks will be bent. And if you look at it, if this is truly to scale, this would be a large amount. But this will happen in real life where the road will crack, it'll shift, and the railroad lines have to be redone. So we do have railroad tracks that go over the San Andreas Fault. Otherwise, we'd have no train tracks or train service going from the rest of the country to Southern California. And the last question was, is this type of fault caused by tension, compression, or shearing? Well, if you look at your notes, it's tension. And again, make sure you consult your earthquake notes when you're doing this lab. It'll help you out. But it's definitely normal faults are due to tension. So you might say, why tension? Well, as these different plates, or not different plates, but different sides of the fault, as they're moving away from each other, and they could be different plates, they don't just move away and create this huge gap. What one will actually do is slip down, and by slipping down, if we looked at it right here, if I was to take and move my cursor straight up, you see how it's over away from this side right here? So even though you might say, well, they're still touching, it has moved. And otherwise, they're going apart, they're going away from each other. That creates tension like a rubber band pulling. So let's go to concept number 2. Concept number 2 said, locate point C and D, and then move point C next to D. So now you can see you shifted the other way. You shifted up, right? So which way did point C move relative to D? Well, this time it was up. The last time it shifted down. Now we're shifting it up. So what happened to the rock layers X, Y, and Z? Well, they shifted vertically. Again, they're not moving horizontally, but they're shifting up and down vertically. Although there's going to be a little horizontal movement as well. So are the rock layers continuous? No. Now in this case, when we look at this, what's going to happen? Well, if the river is still flowing in this direction, now you might get a waterfall. Again, the road's going to have a drop off. The railroad tracks are going to be bent. They're going to be broken. And then finally, what type of force is associated with this? The actual question is this type of fault caused by tension, compression, or shearing? It would be a compression force. And you might say, well, why? How is that? Well, look where this is right here. So if you look where my cursor is, or my mouse is on the video, if I come straight down, you can see that it has moved. It has come closer together. So this would be created by compression forces, things coming together. Now the third concept was to create a strike slip fault. And that was this right here. And it said move point F so that it's next to point G. So we moved F so that it's next to point G. So theoretically this was still, and then we moved F. So if you were standing at point F and you were looking across, so the question is, if you were standing at point F and looking across a fault, which way did the blocks on the opposite side move? Well, if you look at the scale here, it would appear as if they were moving to the south. So again, you had to move F to G, so it'd be easy to see, well, it's not moving. It's said to move F so that it's next to G. But relative to where you were, which way did it seem it moved? It moved to the south, or if you said to the right, I'm fine with that as well. So what happened to rock layers X, Y, and Z? This time they shifted horizontally. They're not going up or down, but they're shifting to the left and to the right. So are the rock layers still continuous? I put yes, you can make that argument. If you look from the side, they should still match up. But if you said no, you're right as well, because they're not going to necessarily, rock layers aren't always going to be perfectly flat and perfectly level, so they still match up with each other. So if you said no, I understand why, and I agree with you for that as well. So what likely happened to the river, the road, and railroad tracks? Again, the river is going to be redirected. You can get some flooding. The roads can be split apart. The railroad tracks will be shifted. Now here's where you're going to have to do a little measuring. If the scale used in this model is 1 millimeter equals 2 meters, how many meters did the Earth move when the strike-slip fault caused point F to move alongside point G? I measured it to be 20 millimeters. So 20 times 2 is 40. If you were really close to that, if you were, 38, if you were 42, that's really good. If you were 40, that's amazing. If you're a little bit further off, 36 to 44, it's still not too bad. However, if you're way off, you struggle to measure, and you might want to work on those measuring skills. Now, the last question here, is this type of fault caused by tension, compression, or shearing? This is your shear force. This is where you got your lateral forces. And we've heard of shearing force in the past when we were studying bridges. So the last thing you have to do is the application questions. So question number 1 says, what kind of fault would you expect to find in the Himalaya Mountains and why? Well, you'd find a thrust or reverse fault. It's a convergent boundary, which means the compression forces are at work. The two plates are coming together. So it would be a thrust or a reverse fault. The next question asks, what kind of faults would you expect to find along the Mid-Atlantic Ridge and why? Remember, the plates are pulling apart. So here you would have a normal fault because it's at a divergent boundary where tension forces are at work. And the last question is, what kind of faults is the San Andreas fault? Well, the San Andreas fault is a strike-slip fault. Now, the second part of it is California likely to fall off into the Pacific Ocean? No, it's not going to fall off into the Pacific Ocean. It's moving horizontally. It's not vertically. And a lot of times you'll hear people talking, oh, California is going to fall off into the ocean in the future. It's not just going to, get to the point where it just tips over and falls off. No, but it's moving horizontally. So at some point in time, yeah, it may not be connected to the rest of North America, but it's not just going to fall off into the ocean. And it's going to take a long time geologically for this to happen, well beyond your lifetime and even my lifetime. So if you have any questions about a model of 3 faults, make sure you ask questions. Thanks.